In this investigation, we wanted to look at the viscous properties of different liquid, water, dish soap, and corn syrup. This can be determined by the constant of viscosity, eta, which is different for various fluids and tells us how viscous they are. Looking at the equation, this relationship is dependent on a variable called terminal velocity, which can be depicted by Vt. We want to know how terminal velocity will change in different liquids depending on how viscous they are, given that the force of gravity pulling on the object is the only other constant force. What should change is the speed of the object traveling through the liquids. We also want to figure out what the relationship is between eta and Vt. We predicted that there would be a smaller Vt for a more viscous liquid and a larger Vt for a less viscous liquid. It is found that the most viscous liquid, corn syrup, resulted in the slowest terminal velocity out of all three liquids we tested.
For the system schema, the only object within the system is the metal ball. The forces acting on the ball are the downward force of gravity from the Earth and the upward resistive force from the fluid it is falling through. When considering the object being dropped as the only object in the system, energy is not conserved. As the object falls, its gravitational energy is converted to kinetic energy, but some of this energy is lost to the surroundings as kinetic energy of the fluid molecules. As shown in the free body diagrams, if the ball reaches terminal velocity, then the gravitational force is equal in magnitude to the resistive force. When terminal velocity is reached, the object has a constant speed and is not accelerating, so the net force is zero. Before the object reaches terminal velocity, the downward force of gravity exceeds the upward resistive force, so the net force is not zero and the object is accelerating. Using Stokes' law, we can plug in the variables that we know for each liquid and solve for what we don't know. In this case, the independent variable is eta, and the response variable is the velocity. When the ball reaches terminal velocity, the force has a constant value equal to the mass times acceleration due to gravity. The radius of the ball was the same for each trial because we used the same metal ball in all three liquids tested.
For our design, the goal was to model Stokes' law by looking at the way a metal ball falling through different liquids is pulled down by gravity. In theory, the ball will represent a system in which the resistant force of the liquid on the ball becomes equal to the force exerted by gravity at the Vt. Using Tracker, we're able to accurately plot the displacement of each ball over time, and using this data we can solve for terminal velocity and compare the fluids. In some of our trials, the magnetic ball displaced some of the water so that an air bubble formed and rose to the surface. This could cause inconsistency with our models because we did not account for air resistance in addition to resistance of flow. Additionally, it was difficult to make sure the ball only moved in the downward direction. Sometimes it would move slightly to the left or the right, which would also be inconsistent with our models in which we only have two forces acting upon the ball.
In our experimental procedure, we filmed trials in which our group dropped a metal sphere into 50 milliliter graduated cylinders filled with corn syrup, dish soap, and water respectively. All three trials were then repeated twice to minimize error. The film was then transferred into Tracker so the movement of the metal sphere in the liquids could be defined quantitatively. The data taken from Tracker was then moved into Excel where calculations were done to find the terminal velocity of the spheres, and to represent graphically the sphere's position over time in all three liquids. The data of the trials is represented graphically here. Each graph was found to have a linear plotline, indicating the metal sphere was descending in the cylinder at a constant velocity. The plotline slope, given in the equation, is an estimation of the sphere's average velocity. The velocity versus time for the metal sphere through the water is described by a negative slope trendline, which indicates that the sphere never reached terminal velocity in the cylinder. The velocity versus time graphs for the metal sphere through dish soap and corn syrup are both described by a flat trendline, which indicates that the metal sphere reached terminal velocity quickly in the fluid. Looking at our data, it can be concluded that the more viscous the fluid, the slower the terminal velocity of the sphere. The data recorded for the sphere falling through the water is the outlier, due to the sphere not being able to reach its terminal velocity in the graduated cylinder. Our observations and data relates to Stokes' law, where viscosity constant is inversely proportional to the terminal velocity of the sphere. Referencing the free body diagram, the net force of the trials containing dish soap and corn syrup is zero, since the velocity of both trials is constant, meaning there is no acceleration, therefore no net force.
Blood viscosity is important because blood needs to flow freely through the body, especially to important tissues and organs, in order to maintain homeostasis. There are certain diseases that are caused by changing blood viscosity. For example, polycythemia is caused by increased red blood cell production in the bone marrow, and it can make blood up to 10 times as thick as it normally is.
Viscosity of rocket fuel must be relatively low so that when the rocket reaches high speeds, the fuel will not alter its density too much, which would cause the rocket to slow down. Rockets must reach a specific speed to even exit the atmosphere. Also, viscosity depends on heat. In space, temperatures vary immensely, so the rocket fluid has to have a low enough viscosity so that it is able to flow and combust in space even under extreme conditions.